A very good afternoon to one and all present here. I, Jayati Arora, on behalf of Amity University, extend a warm welcome to all the honored dignitaries and attendees present on this platform. With the blessings of Honorable Founder President Dr. Ashok Sir and dynamic leadership of President and Chancellor Dr. Atul Chauhan Sir and Additional President and Chancellor Dr. Asim Chauhan Sir, and with the support of our group Vice Chancellor Professor Gurinder Singh and Vice Chancellor Professor Balvinder Shukla, we are honored to welcome you all at this deliberation on global warming and climate change, sustainable adaptation and mitigation strategies, organized by Amity Global Warming Climate Change Cluster on the occasion of World Earth Day 2023. Vasudhaiv Kutumbakam, or One Earth or One Family for Enriched Future. The theme for Earth Day 2023 is Invest in Our Planet. It's time to raise environmental awareness and create consciousness around the issues that affect Mother Nature during this time of crisis. Every April, leaders and environmental activists from all over the world join hands to create sustainable development and offer climate solutions to minimize our carbon footprint and prevent further harm to our planet's natural resources. It is increasingly important to observe this month as Earth starts to unravel the harmful effects of climate change, which not only poses a threat to our existence, but it is irreversibly damaging all forms of life. This webinar is unique in current scenario as globe is facing sustainability challenges along with Earth because of pollution, global warming, climate change, and compounded by the effects of rapid industrialization and urbanization. It is high time to check this increasing problem of pollution on the planet. Otherwise, the time is not far when we will all must bear the precautions, the consequences of this deteriorating Earth. The key to success of this webinar lies in the sustained involvement of national and international experts, academicians, researchers, policymakers, students, and committed common masses. Now, it is my privilege to invite Professor Tanu Jindal, Group Additional Pro Vice Chancellor R&D, Amity University and Director, Amity Institute of Environmental Toxicology, Safety and Management, to open this session. Professor Jindal is a renowned environmentalist, educationist, and scientist with over 25 years of experience. She has completed 12 projects and 9 patents with various national and international fundings in Antarctica, ocean, river and groundwater, air, land pollution, and toxicology studies. She and her students have been awarded many times from the American Chemical Society meetings. She has traveled extensively across the globe, presenting over 120 papers in prestigious conferences. She has several publications in referred journals and 6 books to her credit. She is a fellow of National Environmental Science Academy and has been conferred Scientist and Environmentalist Award. She has recently been awarded with the Women Achiever Award 2022 by ESTA, Distinguished Scientist Award 2023 by NASA, and Women Excellence Award by International Conclave on Material Energy and Climate Award at Indira Gandhi Technical University. Professor Jindal is a Green Ambassador and follows passion of protecting the planet through environmental education and research. She is contributing towards R&D in all the campuses of Amity. Welcome, ma'am.
Thank you, Jayati, for such generous introduction. First of all, I welcome our esteemed guests, Dr. Rupa Kumar Kohli, Dr. Krishnan. Dr. Jagveer would be joining us soon from Ministry of Earth Sciences. And also Dr. Kunal Satyarthi. He has just landed in Joshimath. He called me and he'll be joining in the end of the program. With the blessings of our Honorable Founder President, Dr. Ashok K. Chauhan, we have gathered today to celebrate this World Earth Day. Today is a holiday though, on account of various festivals also, Akshaya Tritiya and Eid. I wish you the happy festivals also. But this World Earth Day is very important in current context when existence of human being, life and planet is in danger because of global warming and climate change. And today we have gathered to discuss about sustainable adaptation and mitigation strategies to combat the global warming and climate change. It is high time that we should all gather together for this noble cause so that our future generations can live happily. I have written a small poem on this day. I will like to quote few lines. In the whisper of the wind and the rustle of leaf, a plea for harmony, a call to retrieve. The earth, our home, a treasure so pure, a sanctuary of life we must secure. Let's rise as stewards with hearts so kind to protect our planet, a mission to bind. Conservation, our creed, our guiding light to keep our world thriving with all our might. Let's heal the wounds of nature and preserve its healthy beneath the scars. The oceans are lifeline, a vibrant source. Let's save them from harm with unwavering force. The forests, lungs of the earth, a refuge for all. Let's protect their splendor, both great and small. The creatures that roam, the birds that soar, their habitats a treasure to adore. Let's strive for peace with love and care for our planet and people. Let's be aware. Let's bridge divides with understanding and grace, embracing diversity in every place. For a world at peace, we must unite with compassion and empathy shining bright. Let's join hands across land and sea to safeguard our planet for you and me. So the poem is little long, but I have conveyed my message that we all have to join hands and work together to save this planet, to save our planet Earth. This is a long poem which I wrote. So few lines I've taken. And also I like to mention about, because of the global warming and climate change, natural disasters are occurring, on which Shri Kunal Siddharthi would speak. But a small few lines were also written on this. Though we say that this is God's uh, anger, but basically all natural disasters like drought, flooding are becoming man-made because of use of natural resources in very unhealthy manner. In fact, our Honorable Founder President, Dr. Ashok K. Chauhan, has started a cluster on global warming and climate change. It studies the impact on extreme various weather, dirty air, water pollution, health risks, rising seas, endangered ecosystems, etc. MIT Universe has a vast knowledge resource of various faculty members available in each campus who are contributing in dealing with these global problems through science and technology. The scope of the cluster is very vast: environmental sciences, pollution, climate change, ecosystem, agriculture, public health, AI and modeling, renewable energy, green energy, sustainability, forestry, wildlife, AGRS, remote sensing, etc. So the cluster has various components on high resolution climate models, weather extremes and climate variability, then biotic and abiotic stress tolerance, then biofuel, bioplastic, biosurfactants for eco-friendly products, then bioremediation technologies. It also takes into account air, water, soil, noise, pollution, etc. Further, the last group deals with solid waste management, heavy metal toxicity, and removal. So we have handpicked the faculty from every campus, and they work in consortium to find the solutions on each and every niche. We are one of the biggest in environmental science domain in India. We have several institutes addressing all the areas of environmental concerns: environmental toxicology, safety and management, environmental sciences, natural resources and sustainable development, geoinformatics and remote sensing, global warming and ecological studies, wildlife and forestry, then green technologies, water technologies, Antarctic research and studies. We are also working in polar region, environmental health and sciences. We have various programs and we have huge human resource. We are generating green ambassadors, right from PhD, MSc, BSc. And along with this, we teach all undergraduates across the campus 4 credit course of environmental sciences, which are mandatory by UGC. Environmental conservation is not a choice, it's a necessity. We must protect our natural resources, preserve the biodiversity, and restore degraded ecosystem, reducing carbon emissions, transition to renewable energy sources, and adopting sustainable practices in agriculture, industry, and transportation. The state of world demands our attention, our action, and our unwavering commitment to environmental conservation, climate change, mitigation, and fostering peace. Because our forests are shrinking, our oceans are choking with plastic, our air is polluted, our wildlife is struggling to survive. Climate change is all driven by human activities and it's wreaking havoc on our planet with extreme weather events becoming more frequent and severe. The consequences are far reaching and affect all of us regardless of nationality, race, or religion. In G20, the slogan given is Vasudhaiv Kutumbakam. So we all should come together to save our planet Earth, and we should use the knowledge and technology resources which already are there to make collective effort to save to by sensing the urgency. It's not a distant threat. Climate change is a reality. And we must acknowledge the scientific consensus, listen to the voice of the most vulnerable, and take bold and decisive action. We must reduce greenhouse gas emission, adapt to changing climate conditions, and support climate resilient communities. Also, invest in green technologies, promote innovation, and foster international cooperation to tackle these global challenges together. Peace is not an abstract concept, it's an essential condition for sustainable development. Environmental degradation and climate change often exacerbate social and political conflicts, displacing communities and threatening human rights. We must promote peaceful solutions, resolve disputes through dialogue and cooperation, and address the root cause of environmental and climate related conflicts. In fact, the solution to all these problems for sustainable development is circular economy, where we use the byproduct also again as a raw material. Earlier, it was a linear economy, consumption, 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 but now we say that reduce, reuse, and recycle, and waste is not a waste, it's a resource at a wrong place. So by following the principle of circular economy, we can really save this planet in every system. In fact, from a starting point where we recognize people need peace, the circular economy can be set up to provide a basis for a world with a culture of peace. In fact, our resources are abundant and available to all. The ability to make a decent living within natural limits come into everyone's grasp. A culture of peace is even a culture of peace with each other. By eliminating the need to struggle all day, every day, just to meet basic needs, gives people more time for personal growth to find peace with themselves. Much of the conflict in society are eliminated when people's basic needs are met. I've already spoken on sustainable environment restoration for peace, and I would like to highlight some of the technologies which are there for sustainable solutions. These are the patents being filed on herbal pesticide and also method for emission factors development, photochemical method of degradation of persistent pesticide, and also simple lab usable lysimeter, low cost water testing kit, etc. So these are some of the patents, and several books have been written by MIT fraternity in published journals, very renowned journal like Springer, etc. Time to time, we keep generating awareness. We have carried out various projects with various ministries also, Ministry of Earth Sciences, Ministry of Environment, Forest, DST, CSIR, etc. on current burning topics. And you can see photo of our Honorable Founder President and our Chancellors, Dr. Atul Chauhan and Dr. Asim Chauhan, and Dr. Gurinder Singh, our Vice Chancellor, Group Vice Chancellor. So we keep doing large number of awareness programs, and this is one of the extension of that awareness programs we keep doing. Our Honorable Founder President Dr. Ashok K. Chauhan again. So these have been carried out with the support of various agencies and inviting eminent scholars and various high-profile people in these planting drives at Vigyan Bhavan. We join hands with various eminent agencies. This time we have joined hands with Ministry of Earth Sciences, IITM, and also IMS Society. I am grateful to Dr. Krishnan and also Dr. Jagveer Singh and also Dr. Rupa Kumar Kohli for the association in this program today. We have been doing large number of environment days, for example, Water Day, Earth Day, then Environment Day, and then Ozone Day, Ocean Day, Environmental Health Day, etc. So we have been celebrating these days to sensitize masses towards their duties. We also participate in various conferences, seminars being organized nationally and internationally. In COP also, we show our presence. This is COP 14. And we have also traveled extensively internationally for joining hands with various agencies for the project and research work. We also launched a campaign on nurture indoor plants, where everyone is been asked to nurture at least 5 indoor plants which are generating oxygen and giving lungs to home. And our campaign, Say No to Firecrackers, is very successful, wherein students have been successful in convincing residents for having a feast instead of burning firecrackers. Going the bicycle way is also a motto to save energy, save environment, and gain health. These are some more conferences we have carried out, and I'm looking forward to hear to our esteemed guests and speakers for their views on the Earth Day. Thank you so much. Our punchline is save Earth to bring worth for the new world. Thank you.
Thank you so much, ma'am, for your kind words and for setting for the day. Let us have the curtain raiser now.
Thank you for sharing the curtain raiser. Now please invite the next speaker.
Earth Day should encourage us to reflect on what we are doing to make our planet a more sustainable and livable place. With these words, now I would like to welcome Professor Dr. D.K. Pantopadhyay, sir, Chief Advisor FPO, Chairman of Amity Law School, Mentor Amity Institute of Environmental Sciences, Amity University, Uttar Pradesh, to address the session and share his views on the topic for today's deliberation. Sir, we are most honored to have you here. Welcome, sir.
Thank you, Jyoti. Now, Amity Group, who are working on the natural resource management, I must give them all my high appreciation, because we do not leave anything related to environment, either in terms of their research, in terms of their celebration, in terms of creating awareness, and also going to the field for doing the extension services. So all my high appreciation towards AITSM and AIES, ASNRD, and AIFW, whole domain of natural resources, which has been created by our Honorable Founder President, Dr. Ashok K. Chauhan. Now, at the outset, I welcome Dr. Rupa Kumar Kole and Dr. R. Krishnan, very eminent meteorologists in the country, talking about, researching about, dreaming about how to create climate smart society and how to create or how to maintain the Earth climate system. So thanks to Dr. Tonu Jindal for inviting me to be here. I think she has forgotten to mention that I am also mentor to your institution. Nevertheless, I think we have to wait for Dr. Jagmeet Singh. I don't know whether she has joined or not. And Kunal Sattarthi, I think he's also going to join. I have a few thoughts for the benefit of our students in a celebrating mood. If we keep up the news, likely all of us know about rising temperatures threatening food and water supplies across the planet, making hurricanes stronger, tornadoes stronger, stretching droughts out even longer. That today, if you just look at in the month of April, the temperature that has risen, 2 states of India, which are supposed to be mild summer states, they have now had to declare the school to be closed during this last 2 weeks. So the changes we are finding is visible now. Only last week there was a huge amount of tornado that took place in United States of America and killing many people. So these are all after effect of the rising of the temperature. So clear signs of a changing climate happening right here, right now. And even though it is present days we are talking about, we can learn an important lesson from history. That lesson, when nature speaks clearly, we better listen and respond. When nature speaks this clearly, we better listen and respond. When we excavate the remains of the past civilization, we very rarely find any evidence they, as a whole society, made any attempt to change in the face of a drying climate, a warming atmosphere, or other changes. And I view this inflexibility as the real reason for collapse. As the ancient Mayan, Khmer, and Manyam empires, among so many others, discovered inaction on the face of changing climate can lead to catastrophe. So what are the ways we can respond, and how do we choose between them? One crisis, to me, 2 responses. One is adaptation, another is mitigation. Imagine you are in a ship that is sinking because of a leak. If we want to stay afloat, we have got to act. The first thing what we could do is grab a bucket and pour water out as it gushes through the hull. This response is adaptation, addressing the effect, the water in the boat, but not the cause of the problem, that's the whole. So adaptation all the time, try to find out the immediate solution so that we remain afloat. In the climate world, the IPCC defines adaptation, the process of adjustment to actual or expected climate and its impacts. It's doing what we can do to live with and minimize the destruction and suffering that comes from climate change. Because to be clear, we have to adapt. To choose just one example, seas are already rising. Now scientists project that the cities and land currently home as many as 120 million people approximately could be underwater, and high tide of 2050 if current emissions continues. failing to adapt to the reality we know is coming, and in many ways is already here. To prevent widespread misery and death is not just irresponsible, it's a criminal, especially when you know that the worst climate impacts hit poor families and people of color the hardest. The bottom line is this: we have got to build homes and infrastructure that can handle the stronger storms and floods on the horizon. We have got to figure out how to feed billions, even as global warming slashes farm yields, turn staples, crops into junk food, and transform where you can grow, and so on and so forth. Potential climate adaptation span a variety of sectors, from agriculture to coastal to urban and many more. Some strategies include building seawalls, elevating infrastructure, or retreating from low-lying coastal areas altogether. In some of the states, for example, cities like Charleston, Houston, Miami, San Francisco, they have created $1 billion investment to protect their seabound populations. Reducing and recycling water use due to drought. For instance, Spain, which has lost 20% of its fresh water in the just past 20 years, has made significant changes to its national water policy. Similarly, in India, the crisis is also visible, and the government, Jal Shakti government, the way they are going ahead in terms of creating Namami Gange project, investing a huge amount of money, using prescribed fires to prevent uncontrollable wildfires. And taking into consideration in Indian context, every year the forest fire takes place. It creates a difficult type of situation for the wildlife. And in the mid-century, NOAA suggests that the risk of every large fire weeks will increase by 300%. Fourth, favoring drought-tolerant crops like rice, cowpea, maize, just as many African countries have done in response to the decreasing rain. All this example and most of human history show we are pretty good at responding to environmental changes when we put our heads to it. However, we cannot stop there. We cannot adapt our way out of this crisis, especially not with the absolutely unprecedented rate of change we are seeing now. Truly solving the climate crisis calls for mitigation. Now, if we just look at climbing back abroad, our sinking ship, the example which I cited, if adaptation is pouring water out to stay afloat in the moment, sealing the leak to halt more water coming in its mitigation. In other words, it is addressing the root cause of the problem rather than dealing with the effects. In a climate context, as the IPCC described, mitigation is human intervention to reduce the sources or enhance the sinks of greenhouse gases. In practice, mitigation can take a variety of forms, including replacing greenhouse gas emitting fossil fuels like coal, oil, and natural gas with clean, renewable energies like solar, wind, and geothermal. With renewables coming, the cheapest form of the new electricity generation across 2/3 of the world in 2019, compared to in just 1% of the world 5 years ago, this measure has quickly gone from a dream to an everyday reality. Second point, replacing traditional internal combustion vehicles with the electrical option, ideally charged with renewable energy. Just like renewables, electrical vehicles are looking better than ever. As Bloomberg NEF describes, over 2 million electrical vehicles were sold in 2018, up from just a few thousand in 2010. Third point, retrofitting old buildings to make them more energy efficient in fast-growing industry worth $3 billion globally. Then planting trees and preserving forests so they can absorb and store more carbon dioxide from the atmosphere. Just like the other strategies in recent years, tree planting has seen unprecedented action by governments and private groups alike. In 2007, for example, the Indian state of Madhya Pradesh planted 66 million trees in just one day. These are just, for example, but we have dozens of tried and tested ways to reduce our greenhouse gas emission. So given those two choices, how do we decide which way to go? Then why these differences, mitigation and adaptation, these differences matter? The truth is, we have reached a point where no single one of these paths will get us to a truly just and livable future. As the IPCC made clear in a recent report, many adaptation and mitigation options can help address climate change, but no single option is sufficient by itself. Effective implementation depends on policies and cooperation at all scales and can be enhanced through integrated responses that link mitigation and adaptation. The scientists are right. We need all hands and solution on deck. In case of our sinking ship, we have got to both seal the lake and pour water out if we are going to avoid sinking. Here is the thing, though, these two solution paths are far from the equal. Both may protect people from a changing climate, but they have different outcomes. The reason? The two words, that is climate justice. Ultimately, all countries around the world, regardless of the size or wealth, have limited resources they can use to respond to the climate crisis. From a policymaker's perspective, adaptation is a local, private good with open, clear, and immediate benefits. On the other hand, mitigation is a global, public good with faraway benefits, which leads most nations from an economic perspective to choose the former option. The real outcome of these two choices present a clear moral dilemma. Author and climate experts, they breaks down this predicament in different forms of writings, ethics of mitigation, adaptation, and geoengineering. So far, many rich countries seem to be unwilling or unable to carry through radical measures to hold back greenhouse gas emission. As a result, many people, especially in the poorest countries in the world, have experienced and will increasingly encounter adverse climate change effects on health, both in terms of morbidity and mortality. The reality, as has been explained, is that while the countries have the power of choice, they can bear the cost of reducing their emissions to the benefit of the world, or they can just choose to adopt, ensuring their short-term security while leaving everyone else behind. So far, they are largely chosen to avoid mitigation. This is not just a problem for today, through, as Gurdjieff goes on to explain, it's a generational justice issues as well. Kicking the can down the road in relation to mitigation, however, also means that future generations will have to bear the brunt of climate change. This triggers intricate questions and intergenerational justice. Our lack of success to curb greenhouse gas emission seems to be compromising the right to life, liberty, and security of a person. He is right. Failing to mitigate our emissions today is leaving this problem, or really a worse version of it, for our children and grandchildren to deal with. Although mitigation and adaptation are both necessary now, the less we choose to mitigate today, the more adaptation we'll need later. Adaptation that will become progressively less effective use as storms simply overwhelm seawalls, for example, an adaptation that many developing countries already struggle to afford given just today's climate impacts. All of this said without even mentioning the potential for dangerous feedback loops. A very possible scenario where if current emissions continues, warming temperature unleash irreversible changes across the earth, like melting Arctic permafrost, releasing gigatons of heat, trapping methane. In turn, these events could unleash even more warming and as a result, even more climate impact. There is only one moral answer. Though we must adapt today, we must truly solve the problem by mitigating our greenhouse gas emissions as quickly as possible. Now, on this Earth Day celebration, to save our planet, to save our Earth, let us put our head together, brain together, resources together, because although there was a climate financing concept that was decided in some of the world conventions, but not a single penny has been given to the developing countries for mitigating, for taking care of the mitigation problem of the greenhouse gas emission. So money is necessary if we want to do all sorts of research. Money is necessary if we really want to create the facilities in different parts of the country. I hope the world leaders will awake quickly and will see that if you want to make a net zero emission, even India has promised for 2070 net zero emission, they are targeted 2030, 2050. Now, hopefully, they will wake up and they will see the investment, climate investment must come onto the way so that we can save our planet. So with these few words, I thank Dr. Tomu Jindal for inviting me. And again, on behalf of our Honorable Founder President, who is all the time talks about, he tells two things very, very clearly. You ask the top world leader, what is the problem? He will say, the change of climate and global warming. If you ask China, they will also say the same thing. If you ask Indian Prime Minister, he will also same thing. Now, if you ask us, all of us, those are involved in this field, we shall also say the major problem of the nation of the planet is that today climate change and global warming. How do we mitigate it? Adaptation is easier option, but mitigation is a stronger option. So thank you very much.
Thank you so much, sir, for addressing the platform. You've always inspired us to work towards the planet, and your words were more encouraging. Thank you so much, sir. Moving on to our first speaker for the day, we have a special address by Dr. Jagveer Singh, Scientist G, Ministry of Earth Sciences. He would be sharing his views on this year's theme for Earth Day, which is Invest in Our Planet. Welcome, sir. We are so looking forward to hear from you. Dr. Jagveer Singh.
मेरी फोन पर बात हुई है अभी, वो 10 मिनट में ज्वाइन कर रहे हैं सर अभी, तो आप नेक्स्ट स्पीकर कॉल कर लीजिए.
ओके मैम. The next speaker for today is Dr. Rupa Kumar Kohli. Dr. Kohli is currently an honorary scientist at the International Monsoons Project Office, located at the Indian Institute of Tropical Meteorology, Pune, India. Prior to his association with IMPO, Dr. Kohli had served as the Chief of World Climate Application and Services Division at WMO Secretariat, Geneva, Switzerland. During 2006 to 2019, he is currently a Vice Chancellor of WMO Standing Committee on Climate Services and co-leads its expert team on CSIS operations. He is a member of the management group of WMO Technical Commission for Weather, Climate, and Water-related Environmental Services and Applications. He is also a founding member of the Managing Committee Global Heat Health Information Network and a member of the Vulnerability Impacts, Adaptation and Climate Services Advisory Board for the Coupled Model Intercomparison Project. Dr. Kohli received his PhD and MSc degrees in meteorology from Andhra University, Visakhapatnam. Dr. Kohli is a life member and fellow of the Indian Meteorology Society and is currently serving as the president of IMS National Council elected for the term 2022 to 24. He would be talking on the topic towards a climate smart society, role of climate services. Welcome, sir. Over to you.
Thank you very much, Jayati, for that generous introduction. And let me share my screen.
Welcome, Dr. Kohli. We are very eagerly looking forward to the very worthy topic we have chosen for the day.
Thank you. Can you see my screen?
Yes, sir. It is visible.
Yeah. Let me first thank the organizers for inviting me to this very important occasion. And at the outset, let me convey my greetings on the World Earth Day, not only from myself, but also from the Indian Meteorological Society, which I represent in terms of leading the National Council. And in fact, the previous speakers, Professor Jindal, as well as Dr. Bandapachai, they have effectively described the problem that we are facing. So let me try and look at some of the ways forward for us to deal with the problem in the way science can address. And in fact, much of my presentation will be based on my experience in working with the World Meteorological Organization for almost a decade and a half, where I was actively involved in the development of climate services. Before that, let me give you a brief introduction about the Indian Meteorological Society. Many of you may not have been actively involved in the IMS programs, but I thought this will be a good occasion to let you know about IMS, which was established in 1957 at the time of the Indian Science Congress. And in fact, I still get goosebumps when I look at the names in the National Council, the first National Council, 57 to 59, where you can actually see the names of some of the legendary and outstanding scientists of Indian meteorology. So that is the rich legacy that we have with the Indian Meteorological Society. We have more than 3,600 life members and about 30 chapters, local chapters in individual cities around the country. And we publish a scientific journal, Vayumandal, and we also publish a number of books dealing with different aspects of meteorology. And one of our annual flagship event is the TropMet, which also takes the form of an international event called Intromet once in 4 years. And we have been organizing this for the last 2 to 3 decades. And the upcoming TropMet is actually at Jaipur. And I'm very happy to see that MIT University is actively involved in its organization, and which is a great thing. And I hope this will help us to build linkages effectively, given the broad coverage of MIT University and its institutions to deal with various aspects of meteorology. I think it is high time that we have a strong bonding between MIT University faculty, students, and the Indian Met Society. And we also have a number of national and international partnerships that we use to build linkages with the experts around the world, and also give visibility to our experts in the world scene. And we also have instituted a number of awards and fellowships to recognize outstanding achievements in the field of meteorology. And of course, our local chapters have their own ways of contributing to IMS activities in terms of a number of workshops, symposia, publications, and also outreach. And in fact, the IMS Pune chapter has recently organized some events to celebrate World Earth Day. So it's nice to see that these activities are progressing very well. So I encourage the people who are actually attending this event to visit our website and see if you are interested in becoming a member and contributing to IMS activities. And coming to the topic of our my presentation now, as we have seen in the earlier discussions, we know that climate has never been constant. It always varies on a number of space and time scales. And in terms of the time scales of our interest, particularly from the point of view of human society, what we see is up to 100 years also. We have a number of ways in which climate varies, and these are irrespective of the so-called anthropogenic influences. We know that the climate varies, and we have to use our knowledge about climate, the way we observe and the way we have developed techniques to foresee the future, to deal with all the climate sensitive activities that human society has been involved in. So in fact, as part of this, I always recall a very inspiring talk by our Honorable Prime Minister, Shri Narendra Modi ji, almost 15 years back, when he was Chief Minister of Gujarat. He actually inaugurated an event on climate services. And he actually articulated that the modern lifestyle actually has evolved as a way of controlling or manipulating or exploiting nature. Whereas our traditional approaches actually try to evolve to live in harmony with nature. So this is where he actually cautioned that nature always wins. We can never control nature. So it's very important for us to actually try to find ways on how the climate is varying and adjust ourselves to live in harmony with nature by avoiding harmful impacts and also exploiting opportunities provided. So the emerging opportunities in terms of societal response and also so-called sustainable development actually demands that the society be climate smart. A climate smart society is that which is resilient to the impacts of climate variability and change, and at the same time pursues sustainable development pathways. So in that sense, we need relevant climate information to enhance policy decision-making, which involves data analysis, monitoring, prediction, etc., which of course should be focused on user requirements. And also at the same time, climate risk modeling tools to understand how climate impacts our activities and what decisions we can take to deal with the climate risks. And in this context, we have to recognize that there is a significant diversity in the supply and demand of climate information. On one hand, you have the needs, requirements, and capabilities of the information providers, mostly the meteorological services or related entities, and also the needs, requirements, capabilities of users to actually access and also apply the climate information for their policy and decision making. So achieving a climate smart society needs to understand these aspects, and we put ourselves with ambitious goals and also comprehensive plans and also collective action from for the whole range of individuals to governments and from local to global scales. That's how we need to work towards a climate smart society. Another thing that we have to note is that there's a lot of climate information that is actually available nowadays, particularly on the internet, social media, etc. But unless climate information is used for a specific decision making, it is of little value. It's not enough to actually satisfy an academic curiosity in providing climate information. So we need to make sure that, in fact, a service is the service only when it is used. So that is where the climate scientists actually enter into the domain of risk management, where you understand how these decisions are made in terms of climate sensitive aspects, and where you move from a kind of mathematical uncertainty where randomness with unknowable probabilities. You move towards randomness with knowable probabilities. We actually see users are not risk is not strange to users. They always deal with risk. So it's very important for us to communicate the available science, including the uncertainties, in a way that it can be used in the risk management strategies that are already available. So to actually illustrate this point, I take you through a kind of a hypothetical, at the same time practical example. Let's say you have a city running low on drinking water during a drought season. And if you are responsible for the city's water management and planning, what would you do? So this actually depends on the climate knowledge and its applications mostly. For example, is this a once in 200-year drought or a more frequent once in 20-year drought? That means whether it is unprecedented or it's a usual thing that comes once in a while. And what do the forecasts, particularly from sub-seasonal to seasonal scale, and even long-term projections say? And what are the measures that we can take to actually manage these risks? And do people have the capacity to derive the necessary information from the data? So these are the various aspects you have to look at. This is how the climate services are defined. And looking at the data, again, you go deeper into that aspect. Are the original observations on paper forms or their perishable media, whether we have rescued them adequately and digitized them? So as the methodological community can be justifiably proud of having accumulated huge amounts of data. We have more than 200 years of continuously observed, scientifically measured observations that are available. So we need to make sure that these data are of high quality and that these data are managed and served in a way that people can have easy access to them. So this is the domain of climate data management. And then once we have the data, we need to assess the climate and also monitor. Can you easily put the current drought into accurate historical context? And are you actively monitoring its progression and the associated drought conditions in real time? So this is where the assessment and monitoring comes in. And in terms of future outlooks, there can be sub-seasonal to seasonal forecasts. There can be long-term changes in terms of frequency and also intensity of the droughts. And what's important to recognize here is that we need to provide access to all these reliable forecast products to the concerned agencies. And we have to see whether that access is available and also whether we are able to disseminate to all the key stakeholders. So this is the area of climate prediction, projection, and delivery mechanisms. And then the user engagement, domain comes in, where we need to use this knowledge to adapt and manage climate risks. So can we assess the risk of drought continuing? What is the potential risk of a continued drought condition? And can we actually adapt and plan for managing the relevant risks? So this is where the adaptation and management of the risks come in. There also you need both information on the climate and also information on the user side. And finally, which is an overarching element, that is capacity development, where we need the required infrastructure to produce and access the required data and information products. And also we need people who are sufficiently trained and have the know-how to derive pre-decision support information from the data. So this is in the domain of capacity development. So combining all these aspects, there is a need for us to put all the different dimensions into a framework, which was actually done by WMO as part of the World Climate Conference to set up a global framework for climate services that actually put together a systematic way to develop and build climate services around the world. And to that, what we need to understand, what are climate services? It is essentially consolidation and dissemination of knowledge about the past, present, and future state of the climate system, and identifying the various types and forms of services, including the impacts that are needed to the community, and development and delivery of these range of products to help in climate sensitive decision making, and then finally promoting effective uptake and application of these products. So these are essentially the climate services that we are trying to develop. And at the same time, there are certain prerequisites. I will not go into them in detail. What is important is that they should be available at time and space scales that are the user needs. Many times the information that is available there may not be relevant to a particular decision making. So that is where you need that availability on that scale, and they should be dependable. That means they should be regular and on time. They should be usable, that the user can understand, credible, that the user can actually confidently apply, authentic in terms of being accepted by all the relevant stakeholders. This is a very important aspect. For example, I give you the case of the insurance of agricultural insurance for weather-related disasters. So there, both the insurer and the farmer should actually agree to have climate information source from the same authentic source. So that is where the authenticity comes in. And of course, the services should be responsive and flexible because the user needs will be changing over a period of time, and they should also be sustainable in terms of affordability and consistency over time. So the global framework for climate services was originally conceived to consist of 5 what we call components or pillars. The first one is user interface platform, where the climate information is linked to the user level decision making, and then the climate services information system, which is the operational core of the framework, where all the information is operationally produced and disseminated to the users. And at the underlying pillars are the observations and monitoring, and the research, modeling, and prediction. These two provide the basic input required for the climate services information system. And of course, covering all the 4 pillars is the capacity development, because you know that we need capacities, particularly in developing and least developed countries, to develop all these pillars. The GFCS, of course, all sectors recognize that all sectors will need to be tackled in terms of all the climate sensitive sectors, but going by the priorities available in the socio-economic context, it has initially given priority to 5 sectors: agriculture and food security, disaster risk reduction, water, health, and energy. So there are special activities addressing the applications of climate services in these sectors. And in all these aspects, what we have to understand is that there should be a full value chain of climate services from end to end. So that is from the way the weather, climate, and water information is produced, and how the value is realized in terms of socioeconomic costs and benefits. So that is where it goes through a number of steps or layers. And the first step is actually the service production, which actually transforms into the climate services information system, which actually I'll go into greater detail at a later stage. This actually feeds the basic and specialized services, some basic climate information, which is of interest to everyone. And at the same time, there are some specialized products that a particular sector or a particular decision context needs. So that is where the services are transformed into that user-related dimensions. And then finally, they feed into the user decisions and action, and which lead to outcomes which are expected to be beneficial, either in terms of avoiding a risk or exploiting an opportunity. So that is where the full value chain has to be kept in mind while developing climate services. And the CSIS infrastructure that we considered earlier actually contains a number of layers from global to regional to national and sectoral user level activities. and also in terms of functionality, data analysis, monitoring, prediction, and projection. So these are the two types of layers that are part of the CSIS infrastructure, which we'll go into greater detail now. The CSIS structure, what does it do, and what does it consist of? Essentially depends on the entire climate spectrum. Don't be confused by the busy slide, but this actually gives the overall the wide spectrum of climate variability that we have to contend with, and how we can deal with that from historical long distant past to distant future, how we actually can deal with the climate variations and change. For example, we need to know what happened in the past, and we need to understand what is happening now, and also look at sub-seasonal to seasonal forecast and interannual forecast, a decadal forecast, and finally the future long-term climate change scenarios. There you have to understand that the climate change scenarios are not predictions. They are just scenarios which are dependent on the development pathways we consider in developing those scenarios. So these are the various ways of dealing with. These are produced in discrete form, but at the same time we need a seamless combination of these various ways of looking at the climate information. And finally, the service delivery happens at the country level, where the country level decisions are made based on that information. And at the same time, at the global level also, we need to provide indicators for global policy processes. For example, the global stocktake or SDG or the COP processes. And the outputs that in this big picture are flexibly generated at least three levels: global, regional, and national. That is, first you develop at the global level, which are then converted to regional level information, and finally it is at the national level information. Or sometimes there are only global information available which are directly applied at the national level. Or sometimes you have only global information and there is no other information available at other scales, where you need to value add at the country level and provide the service delivery at the country level. So this is how the CSIS structure is laid out. And in terms of the current status, what we have is we have excellent procedures available for data rescue, homogenization, and also quality control of climate data. And we have climate data management systems which are actually being implemented in many countries. And we have national scale reanalysis, which is to provide the data in a different form, which is based on climate models, and station inventories and metadata, which are important to understand the quality of the data. And in terms of future predictions, we have severe weather and flood forecasts and climate watches to provide early warnings of extremes. And we have sub-seasonal to seasonal forecasts that are routinely being made available, annual to decadal climate predictions that are also started on an operational scale and are being made available. And of course, climate change projections, you are all familiar on how these are being applied for decision making. And there are also other types of products like hazard analysis, drought monitoring, and flood warnings, and also probabilities of threshold exceedance, and also many others. And we also have a number of tools for developing data and also products on these aspects. So to give you a very quick overview of what is becoming available, and also some are already well established. So these are the so-called WMO global producing centers, which are producing climate information on a global scale by a number of advanced countries, including India. So for example, there are GPCs on long-range forecasts, particularly on a seasonal scale. And we also have GPCs on annual to decadal climate prediction, GPCs on seasonal, sub-seasonal forecasts. So these are all centers that are established by WMO with the help of a number of member countries. And these forecasts are freely made available all the countries in the world. So that is the advantage of having these global centers and providing this information in a standardized way, which can be relied upon to produce regional and national level products. And we also have established a number of regional climate centers as part of the WMO network, where the regional climate centers mainly focus on a specific region of their interest to provide a number of climate-related activities on functions and products. And there are also platforms which we call regional climate outlook forums, where countries sharing common climate concerns come together and develop their own forums to discuss and agree on climate-related aspects. So these are also spread all over the world, and in fact, in India is playing a lead role in a regional climate outlook forum for South Asia, which is called SASCOF, which I hope some of you may be familiar with. So the regional approach is actually considered to be a very important aspect in developing climate services, mainly because a focused regional effort is important for systematic strengthening of the early warning services. And in fact, we know that many countries share common climate drivers, and it's very important that all these countries come to a common understanding in interpreting and using climate information so that their policies are consistent. And this is being demonstrated in many regions, including South Asia, which can be upscaled to other regions as well over a period of time. So this is again a schematic of the regional approach for implementing the climate services information system, where we have these 3 layers: global, regional, and national level, and each layer has its own role in supporting climate services, but they have to work in cohesion to make sure that it is their linkages are smooth, and information flow is driving the decision making at different levels. And to help with this, we also support the concept of climate services toolkit, where you have a combination of push and pull. That is, you push capabilities that are available in characterizing the climate variability and change to the users, because some users may not be aware that certain things are possible. There you need to push some information, and at the same time you need to pull the user requirements, that is to understand how users need climate information and try to supply that. So this is the climate services toolkit that facilitates this process in all the core functions, including data management, monitoring, forecast, and projections. And we also provide a lot of guidance on these aspects. For example, this is a WMO recommended procedure for long range forecast, where you can start with the global forecast and work out the local forecast through a number of steps that are important for downscaling that information. And there are also packages available for developing sector-specific climate information products. In fact, I would encourage you to go to this website and see a number of ways the climate information can be packaged to deal with the climate requirements of specific sectors. And at the national level, essentially, we need a slightly different approach. We know that a number of national agencies, which are climate sensitive, should be key partners in developing climate services. And we also need to involve the national and local governments and universities and other research institutions, NGOs, and private-public partnerships. These are all various ways in which we need to pull together. And in most cases, the National Meteorological and Meteorological Service that becomes the primary climate information provider and has the mandate to coordinate this activity. And for example, in the case of India, we have the India Meteorological Department that is expected to play this role. And in fact, this will become easier if we develop a national framework for climate services on the same lines of the GFCS, and where we also propose the concept of national climate outlook forums. In fact, IMD is actively in the process for setting up a national framework for climate services. And I hope it will happen soon, and we are able to achieve this national level coordination in developing climate services in a more effective and participatory manner. And in terms of key messages, I would like to highlight that The climate services play an important, have an important role to play in building a climate smart society. And we have to recognize that despite the advances in climate sciences, there is suboptimal use of climate information in the real world context. And in fact, much of the information that is already available is still not being adequately used, and people are not able to get benefit from that. So, but that you need improved access to the information and also help in applying that. Climate services, in fact, climate adaptation and risk management, they require multidisciplinary and also international collaborations and also exchange of information. So that is very important to ensure. And the GFCS is a major step forward to systematically approach this requirement. And of course, the focus now that we have the global and regional capacities relatively well established, we need to focus more on the national level capacities, particularly in developing and least developed countries to make best use of that. And in terms of way forward, particularly in the Indian context, I think we need to focus more on enhancement of regional products and services. We need to be part of the global efforts in, for example, in the GPC. And I'm happy to say that we already have the designation of a global producing center for long-range forecast, which is established in Pune, which was given WMO recognition early this year. And we have a regional climate center in Pune, and there is also a proposal to have a third pole regional climate center, which is also being developed. And of course, we have the Codex South Asia at IITM, which is actually supporting climate change projection information. And the SASCOF, which is the Regional Climate Outlook Forum for South Asia, needs to be expanded and also to have a more generic climate forum, not just focused on seasonal forecast, but also all related climate aspects have to be part of this forum. And we need to have greater and sustained engagement of the regional partners. The number of partners are actually active, like RIME, CCMOD, etc. And also the research partners. IITM is a major research partner here. And we also have universities, including Amity University, which should be part of this regional and national level engagement. And it's very important to have a kind of consolidation and complementarity of the investments in support of climate services, because if they are disjointed and scattered, then it can lead to wastage of resources. That's where the consolidation and complementarity are very important. And most important is the user forums, where we should facilitate participation of the users in the development of climate services, and also to co-design and co-produce climate information required for their decision making. And at the national level implementation, we need to work more on the partnerships to encourage stakeholder participation in this. I look forward to the National Framework for Climate Services to take shape, and also the national climate forums. And finally, I strongly feel that we need at the state level, and because we have big states which are almost quite bigger than some of the countries in the world. So we need state level climate forums, particularly in their local languages, to take the climate services to the end user level. So that's very important. So with that, I conclude my talk with just a kind of pointer to a recent development by the UN Global Early Warning Initiative, that is Early Warnings for All, which is actually a major UN initiative in which WMO is playing a lead role, and a lot of exciting activities are being planned as part of this. And I hope this will also accelerate the development of climate services in India and also around the world. Thank you.
Thank you so much, sir, for such an enlightening and extensive talk.
Thank you so much, Dr. Rupa Kumar. There are certain questions are there. Kindly stay with us. We will take them after Dr. Krishnan speaks. So from both of you will take the questions together.
No problem.
Yeah. Thank you.
Now I would like to hand over the session to my colleague, Ms. Charu.
Thank you, Ms. Jayati. Mother Earth is so generous and effervescent. If only we give her the chance, She will restore everything in absolute abundance and health. Now, I would like to invite our next speaker of the session, Dr. Krishnan Raghavan. Dr. Raghavan specializes in climate modeling to understand scientific issues relating to climate change, Asian monsoon, and water cycle. Under his leadership, the Center for Climate Change Research, IIT in Pune, developed the first Earth system model from India that contributed to the CMIP6 and IPCC6 assessment report. He was a coordinating lead author in the IPCC AR6WG1 report and a drafting author in the summary for policymakers. He is a member of the Joint Scientific Committee, World Climate Research Program, World Meteorological Organization. He and his team from CCCR IITM published the first National Climate Change Assessment Report of the Ministry of Earth Sciences, Government of India in 2020. After obtaining MSc degree in Applied Mathematics from the Madras Institute of Technology, Chennai, he pursued PhD research in atmospheric sciences at Physical Research Laboratory, Ahmedabad. He was awarded PhD degree from University of Pune in 1994. He has published over 152 scientific articles, supervised 40 PhD degrees, awarded and 9 ongoing and 7 master dissertation. He offered training lectures in geophysical, fluid dynamics, and atmospheric sciences. Welcome, sir. Over to you.
Yeah. Thank you, Ms. Charu. Thank you very much. First of all, happy World Earth Day to everyone. And I want to also thank all the panelists and Amity University and Professor Tanu Jindal for this opportunity. With this, I will just go to my presentation. My presentation will be a bit more scientific, with, of course, the message that we have to reduce the greenhouse gas emissions for a sustainable future. This has been right, the way to sustainable development, this has been there right from our historical times in the Indian history. And I will just, and Dr. Rupa Kumar talked about climate variability. I will also talk about the past climatic variations when the human influence was less and how the monsoons were at that time. And now what the monsoon is undergoing right now. And some of the modeling capabilities that we have developed at our institute to make climate projections and also decadal timescape predictions. I will just highlight that. That will be the overall idea of my presentation. How do I
share your slides?
screen? Yeah.
Share.
So you're able to see the screen?
Yes, sir. It is with
Yeah. Yeah. Once again, thank you for this opportunity. So my today's talk will be on Earth's climate system and Indian monsoon. And so first of all, why do we study the Earth system? The most important thing is life exists on Earth because the climate of the Earth is favorable. That's the most important thing. And Earth's climate system, when we talk about the climate system itself, we are talking about the atmosphere, the ocean, the cryosphere, that is the ice-covered portion of the Earth, the biosphere, that is the vegetation, with the sun being the main source of energy. In fact, when you go to the Surya Upanishad, the importance of sun as being the main source of energy has been highlighted. So from time immemorial, the importance of the sun in the Earth's climate system is well known. Our ancestors understood this very well. And there are natural changes and variations in the Earth climate system, and they can arise from natural forcing. For example, the Sun-Earth orbital changes, plate tectonics, and a variety of other natural forcing mechanisms. So they can affect climate, they can influence the climate system, Earth's climate system, and produce variability. I'll touch upon some of those things. And also various feedbacks among the components of the Earth system, that is the atmosphere, the ocean, cryosphere, biosphere. They can have feedbacks on different time and space scales, and which is what gives rise to the climate and the mean climate, as well as the variations on different time scales. These interactive processes. And life forms, organisms, biogeochemical processes, they are very important for contributing to the carbon, for example, the carbon cycle, and they can also contribute to climate variability. So in addition to these natural variations in the climate system, human activities, especially since the last century, they have altered the Earth's climate system. And this was brought out in earlier speakers' presentation, that climate change is a reality. It is already there, and it is projected to increase in the coming decades, in the coming centuries as well. And so this has been a big threat to humanity, in fact. And so Earth system science, when we talk about Earth system science, it integrates various disciplines. So it is truly transdisciplinary. When we talk about it integrates not just it integrates various subtopics and subjects like physics, chemistry, mathematics, biology, meteorology, oceanography, ecology, geology, environmental science, solar space physics, astronomy, and the various troposphere, stratosphere, mesosphere, chemistry of the atmosphere, the marine and terrestrial biogeochemistry, carbon cycle, agriculture, industry, human activities, economics, social science, philosophy, history, policy, sustainability, etc. So it's very, very important to understand Earth system is really a very, very transdisciplinary subject, Earth system science. And to study Earth system science, one of the important, if you want to really understand how the climate is changing, how it is varying, how it is changing, and what are their impacts, Earth system models, or what we call them as ESMs, they are very important tools. For example, the IPCC projections, they are all based on Earth system models, global climate models, because these are very powerful tools for representing and quantifying the processes within and between the atmosphere, ocean, cryosphere, and biosphere, both terrestrial and marine. And they are important tools for providing information about the physical, chemical, and biological mechanisms governing the rates of changes of the Earth system. So when we talk about the Earth system, as I said, the sun, which is the important source of energy. And in fact, the motto of IMD, when we go back to their logo, it says Aditya Jayate Vrishti. That means sun gives rainfall. So this recognition has been already there long back. And this, so if we want the rainfall, it is very much dependent on the sun. And so much of the solar energy, when it passes through the atmosphere, only 30% or so is reflected by the atmosphere and the clouds. And 70% of that radiation is transferred through the atmosphere into the Earth system, which is absorbed by the land surface, the oceanic surface, also the biosphere. And these in turn emit the radiation in the long wave, in the infrared. I'll come to that in my next coming slides. And once the incoming solar radiation is absorbed by the Earth's surface, it leads to increased evaporation from the oceanic and from the land areas. There is exchange of momentum and heat fluxes from the surface into the atmosphere. And this in turn can contribute to the formation of clouds, producing precipitation. And the radiation also, the radiation that is emitted by the Earth is also affected by, it is absorbed and scattered by various constituents of the atmosphere, what we call as the composition of the atmosphere in the atmosphere. And this is a very, very important part. And this is going to affect the radiation balance in the atmosphere. And also you have natural forcings like volcanic eruptions. They can throw a lot of sulfate aerosols into the atmosphere that can go high in the stratosphere, and they can reside there for a couple of years. And they can also alter the radiation balance in the atmospheres. And of course, when we talk about precipitation, clouds become a very important component of the water cycle. And so when we are really talking about the Earth system, we are talking about the feedbacks among all these different components of the Earth system, and they are happening on different space and time scales. So if we want to quantify the rate of exchanges, the ESMs are very, very important tools to understand how these different components are interacting. And when we change one of the composition, for example, the greenhouse gases like carbon dioxide and methane, what it is going to do to the climate. So it becomes a very, very important tool. And this is what goes in all the IPCC projections and all the coupled model experiments, CME activities. So building this knowledge is very important. So models become very important. And basically, this is a slide that I took from Professor Shukla in one of his talk. When we talk about the climate of a planet, basically it depends on the following parameters. One is the energy from the sun, and what is the albedo, the planetary albedo, how much of the incoming radiation is reflected back, and also the rotation rate of the planet, because that is going to determine the general circulation of the atmosphere, the mass of the planet, the radiation of the planet. Very importantly, the composition. When we talk about the composition of the atmosphere, which involves water vapor, carbon dioxide, ozone, clouds, and also the distribution of the land and ocean, the topography. These are the most important elements that is going to dictate the climate of a planet. So our understanding is, when we talk about the energy, Earth's energy balance, at the top of the atmosphere, we receive something like 1,380 watts per meter squared. This is the solar radiation that comes from the sun at the top of the atmosphere. If you want to work out a simple energy balance, the important thing is the incoming energy should be in balance with the outgoing energy. So the radiation balance is very, very important. So in equilibrium, if we say that, if we work out the simple calculation, we know that 30% of the radiation, so the Earth's albedo is something like 31%. And so that means that is the amount of radiation that is reflected back, incoming radiation, solar radiation that is going to be reflected back. And we know the solar constant, that is the S, that is the total amount of radiation coming at the top of the atmosphere. We know this falls on a disk of radius whose area is pi r square, where r is the radius of the Earth. And so this is the total incoming. 1 minus alpha is the amount of energy that is absorbed, because alpha is reflected back. So the outgoing energy is E into 4 pi r squared, because now we are emitting the radiation from a sphere whose surface area is 4 pi r squared. So if we measure the emitted energy by the Earth, it turns out to be 1 by 4 into 1 minus alpha into a solar constant. This turns out to be about 237 watts per meter squared, which would mean, by going back to the Stephen Boltzmann law, the temperature of the planet would have been 255 degree Kelvin, or minus 18 degrees. But that is not true. When we actually measure the temperature of the Earth, it is, the mean temperature is close to about 15 degrees. Now it has increased by 1 degree. And the measured surface energy is 390 watts per meter squared. So basically what is happening, the difference is there is a greenhouse effect of 33 degree Kelvin. So the mean temperature of the planet is not minus 18, it is plus 15 degrees. So thanks to all these greenhouse gases in the atmosphere, the atmospheric composition, which keeps the atmosphere warm. If the greenhouse gases were not there, we would have ended in a snowball. The Earth would have been a snowball with much, much lower temperatures. Because of the presence of the greenhouse gases like water vapor and carbon dioxide, life on Earth is possible. So the mean temperature is about now, We are close to 16 degrees, 16.1. And this just to give to some of the students who will be interested. As I said, the incoming solar radiation, this is plotted as a function of the radiation intensity across different wavelengths. So the incoming solar radiation is mostly in the visible and in the ultraviolet and the infrared. And when we see the radiation that is going out from the Earth, that is mostly in the infrared wavelengths. And I just shown some of the absorption that happens, the important constituents that are absorbing the radiation. We have some absorption of the ultraviolet radiation by ozone and the oxygen. And but much of the radiation passes through the atmosphere. And there is some absorption of the infrared radiation in the long wave by ozone. But if you see the main absorbers are the carbon dioxide, which is in the infrared wavelength, near infrared and the far infrared, and also in the microwave, and the water vapor. So these are the main absorbers. And this is the total absorption that happens by the different constituents of the atmosphere. So I have plotted three circles. Why I am plotting, these are very important wavelengths in the infrared, which was originally used by the calculation by Manabe and Weatherald, which got the Nobel Prize in 2021. They had just 4 wavelength bands, and they are very, very important. That is going to determine the climate of the planet. One is at around the 6 micron, corresponding to the water vapor. And there's also a water vapor absorption at around 15 microns, and which also overlaps with the carbon dioxide absorption at 15 microns. And there is one at 9.3 microns or so. These are the 4 important bands. And so, as I said, when we look at the fundamental laws of the radiation is governed by the Planck's function. That is the radiation emitted by a black body as a function of different wavelengths. And also for the typical black body emissions at the terrestrial temperatures, this is the kind of Planck's distribution. You can see that with higher temperatures, your black body emission is at the shorter wavelengths compared to the longer wavelengths. And so when we look at these black body radiation emitted curves for the sun, for basically the photosphere, sun's photosphere, which is at 6000 Kelvin, and the Earth's temperature, you can see the sun's emission black is mostly at the visible range, in the visible range. And for example, for the Earth, which is emitting at 288, 15 degree centigrade, it is mostly in the infrared. The Earth is emitting, and we have these absorbers like the water vapor and carbon dioxide, which absorb the radiation emitted by the Earth in the thermal infrared. So the near infrared is typically 0.7 to 4 micron, and the thermal infrared is 4 micron to 15 micron. And this is where all the action is concentrated in terms of the energy exchange and the enormous complexity of the atmospheric absorption spectra. So the thermal infrared is a very, very important even for the satellite meteorology. And just to give you some more insights into the Earth's energy budget, as I said, suppose we have 100 units of energy coming, about 6% is reflected back into the atmosphere, and 20% by clouds, and 4% by Earth's surface. So that's about 30% put together. So remaining 70% passes through the atmosphere. These are all the global estimates, and about 51% is absorbed by the land and oceans and radiated back into the atmosphere. And the outgoing radiation, some of it is infrared radiation, is absorbed by the clouds and by the atmosphere, and which are again radiated back and directly into the space about from the Earth to the space about 6%. And if you see the total balance, what is coming into the system and what is going out, there's a perfect balance. And it is very important for the climate models to ensure that there is a radiation balance between any climate modeling. This is the most important thing that needs to be ensured, that there's a global balance between the incoming radiation and the outgoing radiation. And But this radiation balance is not spatially uniform. So when we take a latitude plot of the radiation balance between the incoming and the outgoing radiation, we see that the tropics, there is more radiation that is absorbed compared to the outgoing long wave radiation. So tropics is a region where energy is being introduced into this earth. And when you go to the higher latitudes, basically there is more radiation loss. Net loss is more. So you have an energy gain into the tropics, net loss from the higher latitudes. So once you have an energy gradient between the tropics and the extratropical latitudes, circulation, this energy imbalance drives the atmospheric circulations and motion. And of course, we also have the Earth's orbit as it goes around the sun. It has a tilt which causes the seasons. And so the temperature, so there's an incoming radiation. It not only varies with latitude, it has a seasonal variation. And this picture shows how the temperatures at the Earth's surface vary seasonally due to the changes in the radiation. So for the basis of the weather and climate models is that we have to basically represent the atmospheric variables like temperature, wind, moisture, pressure on a grid at different levels. And we are basically trying to describe the loss of motion, the loss of thermodynamics, to predict the rate of change of temperature, pressure, velocities, humidity, etc. at different points. And these are all coupled to one another. And these are all coupled through complex differential equations. That's how we have to describe them, because you cannot solve them analytically on a calculator. So this involves millions of computations and depends on, again, that depends on the grid size. If you make finer grids, your computations are going to increase and the number of variables. And also these are typically you start with the initial condition and then you integrate in time these models. And typically these time steps can be of the order of few minutes. Now, as you increase the resolution, the time step also gets smaller and smaller. Your computational number of computations increase. So the computational complexity increase. So in the 1990s, the models were typically had a horizontal resolution of about 250 kilometers. In the present day global models, climate models have a resolution of 100 kilometer grid size and even smaller. Now they're even going to 50 kilometers globally. And they're trying to reduce, increase the resolution, make the grid size smaller. Also in the verticals, more number of levels are introduced in the atmosphere to make these computations. This is just the atmosphere. But when we talk about climate, it's not only the atmosphere, we also need the oceans because oceans cover 70% of the globe. So you have different levels, about typically 50 to 100 levels in the oceans. And the atmosphere and ocean models are coupled to each other. And we also have the ice component, the biosphere. So this becomes computationally very, very challenging. And which is why we then resort to high performance computing if you want to use these models to make climate projections. And one such model we developed from IITM, it is known as the IITM Earth System Model for long-term climate change studies. This was the first global climate model, Earth System Model, first from India. We contributed to the CMIP 6. We made projections, which also went into the IPCC AR6 assessment. And as I said, we have to have a radiatively balanced system. This is a simulation for 500 years corresponding to the pre-industrial conditions before the industrial era, where we have to obtain a radiatively balanced system in terms of the global mean temperatures have to stabilize, the sea surface temperatures have to stabilize, and the radiation balance at the top of the atmosphere should be achieved. And this itself is a first important step. And in fact, the first version of the model which we had, which is known as the ESM version 1, did not have this radiation balance. There was a huge imbalance even with the pre-industrial condition, something like 7 to 8 watts per meter squared. And we found out that this problem was happening because of the increased melting of the Arctic ice. Arctic ice in the model was melting, and this has implications on the deep ocean circulation And once you have problems with the Arctic ice, you develop biases in the sea surface temperature, not just in the Arctic region, also globally. And then your radiation balance is for a toss. So we decided that we should fix this problem of sea ice. So in the next version, which went into the CMIP 6, we ensured that the sea ice is improved. This is one of the important components. We did several other things. We improved the Arctic sea ice, improved the radiation balance. Although it is not, still there are problems with the summer sea ice in the Arctic. There are issues. We are trying to work on that. So the main point is obtaining a radiation balance. And then we made future projections. I'm not going into those details. We also made projections for the 21st century. And we also made projections for the Indian region. This has gone into the this has gone into the assessment of climate change report for the Indian region. This is a report by the Ministry of Earth Sciences, where we looked at the historical changes in the temperatures over India, precipitation changes, sea surface temperature in the North Indian Ocean, sea level changes in the North Indian Ocean, the Himalayan snow cover, and also how the model is capturing these variations in the historical period, all these variables over the Indian region, and also made future projections. What is shown here is for the one of the CMIP 6 scenarios, SSP 245, and this is just to give an idea of what these projections regionally look like. So now I want to come to the main point that how human activity has influenced climate. It is very, very clear. So as I said, when you go back to the paleoclimatic timescales, one of the important drivers of the paleoclimatic variations is the orbital forcing. And this is the current movement of the, when I say of orbital forcing, this is basically the Sun-Earth geometry. So this is the current movement of the Earth around the Sun. We have during July, this is the aphelion, this is the farthest position of the Earth from the Sun. And during January, this is the closest distance, which we call as the perihelion. And of course, the Earth's orbit has a tilt of about 23.5 degrees as it goes around this elliptical orbit, and which is what gives the seasons. Now, there's a very important, this Russian scientist called Milankovitch. He noted that effects in the orbital variations, they can influence the solar insolation and they can influence climate in turn. And he documented 3 important orbital variations. One, the variation arising due to the eccentricity of the orbit. So whether the orbital, you have a more elliptical orbit or less elliptical orbit, this is going to, so these variations happen on a typical time scale of about 100,000 years. And you can also have changes in the tilt of the orbit. The present day tilt is around 23.4. So you can have tilts varying from 24.5 to 21.5. And these variations in the tilt, they happen typically at a time scale of about 40,000 years or so. So basically, as the Earth is going around the Sun, around this axis, and it is spinning, it is basically precessing. And this precession can also vary in time scale. And this is typically something like 19,000, 20,000 years time scales. And so when you go back to these records of, from the deep sea records of the oxygen isotope, they have recorded the climatic variations of when the past, when in the Earth had a glacial period, and you have warm periods known as the interglacials. So these are recorded in the Earth's history, in the deep sea records, which you can identify from the oxygen isotopic variations of these foraminiferas. And people have constructed these different time scales. And now this record is available for more than 3.5–4 million years ago from the deep sea records. And we can understand how the climate has varied due to these orbital changes, how the glacial periods and the interglacial periods have happened. So in that context, when I come about 6,000 years, we call it as a period of mid-Holocene. Holocene typically refers to the last 10,000 years, where we have good understanding of how climatic variations have happened. And this about 6,000 years back, we had the maximum solar insolation, summer insolation on the Earth. And the tilt of the axis was about 0.7 degree more than the present day, and the eccentricity was slightly larger. So because of this, and also the perihelion was more close to the autumnal equinox in the mid-Holocene. That is 6,000. So when I'm saying mid-Holocene, it's about 6,000 years. And solar insolation was maximum in this northern hemisphere. And this is the time there are a lot of proxy records. People have noted that the monsoons were very, very strong. Not only strong, they were very favorable. And many civilizations, Indian monsoon received a lot of rainfall, also the West African monsoon. And so many civilizations flourished, like the Indus Valley civilization, the Mesopotamian civilization, the Egyptian civilization. So there was abundant exposure to water resources. And this is one of our PhD students. She worked with me, Lakshmi Mudra. She has done a nice PhD work. She'll be submitting the thesis very soon. How these orbital changes during the mid-Holocene have affected the monsoons over India and West Africa, for which we used a very high-resolution model, and we did experiments corresponding to the present day, typically the pre-industrial climatic conditions, about 1850, and the mid-Holocene. That was the time when you had the maximum insolation energy in the northern hemisphere. And we used a very high-resolution atmospheric GCM, which we set up here, and the grid size is about 35 kilometers. What we noted was when you have more of this insolation in the north, more radiation, we found that there is more energy input into the system. The monsoon develops, there is more water, more evaporation from the oceans, there is more energy, moist static energy. The monsoons intensify, and the ITCZ starts moving to the north of the equator. So the West African monsoon and the Indian monsoon was really intensified during that time. And also the monsoon circulation strengthened. I'm not going into those details. And so we know that orbital changes can make these big changes in the monsoons. And now people are also trying to, there is also, but when you're talking about several centuries or several millennia, during this long period that you could have also climatic variations, which can be caused by different drivers, like, for example, the El Nino Southern Oscillation. So whenever these El Ninos happen, we tend to get, these are periods when the sea surface temperature in the central and eastern Pacific can become anomalously warm. And El Ninos generally tend to be associated with droughts over India and also parts of West Africa. And of course, there are other modes of climate variability, like the Indian Ocean dipole. And so these modes of variability are happening on the decadal timescale, intra-annual timescale, decadal timescale, and they can affect climatic variations globally and also over the Indian monsoon and the other regional monsoons like the West African monsoons. And so people have reconstructed, this is by colleague Naveen and his team, Fanindra, they have collected these cave deposits from Kadapa in Andhra Pradesh, and they have reconstructed based on the oxygen isotope. They have constructed more than 3,000. This record, first they constructed up to 3,200 years from the backward in time, but they are even going beyond. I was told that they're going to reconstruct this for the entire Holocene, the last 10,000 years. And what we find is during this period, there are these variations in the monsoon on different intra-annual and also decadal, multi-decadal timescales. And we also see how the different civilizations in the Indian region have evolved. And people have developed technologies, they develop techniques to address whenever a drought is happening, how they developed artificial ponds and wells to address these challenges of vagaries in the monsoon rainfall. So the knowledge existed earlier also that whenever these variations are happening, how to deal with them, and development of artificial lakes and so on. And so now what is happening is this is all in the past. Now, since the following the industrial revolution, man as human activities have increased the carbon concentration of the greenhouse gases. This is from the 5th assessment report. The values, and this was during 2011, the values of the greenhouse gas concentration is around This was in 2009 value, around 409 parts per million by volume. But now it has further increased. The latest is 418 parts ppm carbon dioxide, and methane has also increased, and nitrous oxide is also increased. So the increase that we are seeing is happening at a very alarming rate. And this is mainly by human activities. And so it is very, very clear that the increase in the greenhouse gases that we are seeing during the last few decades and since the last century is mainly contributed by the human activities. And so what has it caused? It has led to an increase in the global mean temperatures. And so this is very clearly coming out. It has been, so climate change is real. It is already happening. And when we see the top 3 warmest years was 2016, 2019, and 2020. And much of the warming is not spatially uniform. Much of the warming, we do see them in the higher latitudes. There are feedbacks because of the changes in the ice cover, so you are decreasing the albedo. There is more absorption of the radiation. And so the temperatures are increasing much faster. It is not spatially uniform. And the carbon dioxide is this being monitored at several sites. The most important one, well known, is the Mauna Loa site in Hawaii. So carbon dioxide levels are increasing, global temperatures are increasing. And the 2011, decade by decade, when we see the 2011 to 20 is the warmest decade on record. And in 2021, the global mean temperature is 1.11 above the pre-industrial average. The latest, when we talk about 22, it is 1.15. And all the warmest years are last 7 years. Even the 2022 is among the recent 7 years, which are warmest on record. So climate change is already happening. And the IPCC has clearly, the report says that human influence has warmed the climate at a rate that is unprecedented in at least the last 2000 years. So all these models, Earth system models, climate models, they show that for the historical period, the increase in the observed temperature, you can explain only because of when you introduce the anthropogenic forcing, that is the increase in greenhouse gases, and also the effects of the increasing aerosols, which try to kind of reduce the magnitude of warming. But if you had only natural forcings like orbital forcing or solar and volcanic forcing, you cannot explain this observed warming trend. And this is shown by multiple models. So climate is already warming. And what does it mean? Now, in fact, why do I say this? In fact, the 2021 Nobel Prize, the pioneering contribution by Manabe and Weatherall, the 1967 paper, that was the first climate model. He explored the interaction between radiation balance and the vertical transport of air masses due to convection, and taking into account the heat contributed by water cycle. And so he pointed out the importance of the water vapor in amplifying the global warming. And the other person who shared the Nobel Prize in the climate was Klaus Hasselmann. His work was to identify the fingerprint of the global warming. So he developed methods to distinguish between the natural and human causes of atmospheric heating. And also this Nobel Prize was shared by Giorgio Parisi for, of course, his contribution was to the discovery of the interplay of disorder and fluctuations in the physical systems from atomic to planetary scales. So climate science received a very important contribution, recognition globally. And we know that, as I said, water vapor is a very, very important greenhouse gas. So as the temperatures increase, one of the consequences is, because the temperature depends on the saturation vapor pressure, for every 1 degree of temperature increase, water vapor in the atmosphere increases by 7%. So what does it mean? So if the water vapor is increasing with temperature, the immediate consequence is heavy precipitation will increase. That is what we are seeing now. So one of the direct consequences, globally it is happening even over the Indian region, due to the increase in temperature and water vapor, heavy precipitation, we start increasing, deep convection starts increasing, convective activity. And according to the AR6 assessment, we see that with the warming, global increase in the temperature, with every additional increment in global warming, the extreme weather are going to increase both in frequency and intensity. For example, an event, temperature extreme warming event, hot temperature extremes over land, which used to occur once every 10 years, that frequency is now becoming, present day it is 1.1, it has become 2.8 times more frequent. But with the future warming, 1.5 degree global warming will be reaching in another 15-20 years. And so they will become more frequent, 4.1 times. And likewise, with increasing warming levels at 2 degrees and 4 degrees, hot temperature extremes will increase. Not only that, even the precipitation time extremes over land, heavy precipitation events, they are also going to increase with increasing global warming. And that's a very powerful message, and that is going to happen all regions of the world. Now, what does it mean to the monsoon? Now, monsoon is really, Indian monsoon, it's a very complex dynamical system. It has interaction where you have the Indian landmass, you have the Himalayas, you have the elevated.
Dr. Krishnan, we wanted to welcome Dr. Jagveer Singh. I think he is there. Dr. Jagveer Singh.
Yeah.
Dr. Jagveer Singh, he opened his camera just now.
Okay.
Yeah.
Yeah.
So please carry on. Please carry on.
Okay, fine. I'll try to wind up in 10-15 minutes.
Yeah.
So you have this very huge continental landmass, the Indian subcontinent with the Himalayas, mighty Himalayas, the Tibetan Plateau. And then you have a huge water body, the Indian Ocean, the mighty Indian Ocean. And also you have the adjoining, the African continent, the East African mountains. So this is a very complex. So because of the setting up of the thermal contrast to begin with, you set up the pressure gradients because the temperatures, you have developed temperatures are cooler over the ocean during the pre-monsoon time, high pressures, and there's a movement of air from the high pressure to the low pressure towards the Indian region. Land is warmer, there's a low pressure development, and then you have the effect of the Earth's rotation, the Coriolis force. So the winds pick up over the Arabian Sea, and then there is a lot of evaporation. So as the winds strengthen and the temperatures start increasing, there is a lot of evaporation, there is more moisture in the atmosphere, and the moist air interacts with the Western Ghats. It undergoes forced ascent, produces precipitation, and these clouds also release huge amount of latent heat, and the latent heating can in turn affect the circulation, the winds, they can in turn strengthen the winds. So there is a continuous feedback, interactions between the ocean, the land, the moisture, and also it affects the oceanic circulation. And during the summer monsoon time, you have the upwelling of the deeper waters from the coast of Africa and the Oman coast that brings a lot of nutrients, and which is important for the fisheries, for the primary productivity. It brings a lot of chlorophyll at the surface, the ocean color changes. And so this is really a complex system. The question is how climate change is going to affect. So when we are introducing these greenhouse gases, it's not only greenhouse gases, there are other air pollution, like what we call as the suspended particles or particulate matter in the atmosphere known as aerosols. And they also affect the incoming solar radiation. Greenhouse gases are mainly, they are going to trap the long wave infrared radiation, whereas the aerosol particles, they mainly reduce the solar radiation directly coming from the sun and insolation at the surface. So when you have these human activities, they can really, the question is whether it has influenced the monsoon. So the assessment that came out from the AR6 assessment from our chapter, the global land monsoon precipitation decreased from the 1950s to the 80s, primarily due to the anthropogenic aerosols, because they reduced the incoming solar radiation, but has since increased in response to the GHG forcing and large-scale multi-decadal variability. And in the future, we also assess not only global monsoon, all the regional monsoons, the South Asian monsoon, the East Asian monsoon, the West African monsoon, Australia, maritime continent, North American and South American monsoon. The assessment is that during the 21st century, the global land monsoon is projected to increase in response to greenhouse gas warming in all time horizons and scenarios. This is a very high confidence statement. So as the monsoon, even though the monsoons may increase in mean monsoon, there's
Dr.
also
Jagbir Singh, would you like to speak? Dr. Krishnan, actually, Dr. Jagbir Singh is now organizing a very big function at MOES. So
Okay.
I would request if he can give a message for some time. Dr. Jagbir Singh, we welcome you.
Yeah,
I hope you will not mind.
Yeah, I'm fine. So basically what we are finding is
Sir, we will continue with yours. Can you just ask Dr. Singh to say a few words in between? I would be grateful.
So what am I supposed to, should I stop my talk or what?
Sir, I'm saying just if he can give a message for a while because.
Yeah, so my main message is that basically we have moved from it is important for a sustainable future. We have to transition from a fossil fuel energy to the solar energy. And the Indian Prime Minister during the COP26, he launched this One Sun, One World, One Grid at the COP26 summit. And the formation of the International Solar Alliance was declared. And this is very important for a sustainable future. And with this, I want to end my talk. Thank you for your kind attention.
Sir, we would be having certain questions which we have noted. So please wait for that.
Okay.
Yeah. Yes, sir. Now we welcome Dr. Jagbir Ji. Richard Charu, please welcome him.
Yes, ma'am. Thank you so much, sir. Now I would like to invite our next speaker, Dr. Jagbir Singh, Scientist G, Ministry of Earth Sciences. He would be sharing his views on the year's theme for Earth Day, Invest in Our Planet, Earth Day. Welcome, sir. Over to you.
Kindly unmute, Dr. Jagbir Singh. Kindly unmute. Kindly unmute your mic. Kindly unmute. Your mic is muted.
Yeah, okay.
Yeah.
Yes, sorry, it was muted.
Yeah.
Thanks, Amity University and Professor Tanu Jindal ji. Actually, this was excellent listening, like always.
So you are not audible.
Sir, your mic is muted again.
On model and particularly on climate by Indian Institute of Tropical Meteorology, and they had been part of basically IITM has been part for the IPCC also. So I could listen, and I always enjoy listening him. So thanks for that opportunity. I could listen him again. Then it has been one panorama I could see in your program, starting from your own poem on this, and beautiful poem that was excellent listening. Then other experts, and particularly Dr. Krishnan ji. Just I would like to mention here that ministry always is, that in supporting mode for the particularly awareness on earth and related issues, climate and nature. And the students who are our future ambassador, we try to put forward ourselves rather to them and to get them along for this cause. So this year also, like previous year, we had got many proposals. I would like to mention here, just apprise you that ministry has supported for approximately the proposals about 75 places across country for awareness on Earth Day. And focus of this year had been as desired by Secretary, and as he kindly advised, that was students, girls' college, schools, differently abled ones, and then giving a focus on aspirational districts. So this year, approximately 20 aspirant districts are covered for that. And today, this is also one opportunity for me to invite you all that Ministry of Earth Sciences is organizing one concert by 3-time Grammy awardee Ricky Case, who happens to be Ambassador of India at United Nations for the Culture. So today 6:30 that program would be there. Chief guest would be Honorable Minister chief guest would be Honorable Minister of Earth Sciences, Science and Technology and PMO and Space, Dr. Jitendra Singh ji. Am I audible?
Yes.
Yes, sir.
Okay. एक इसमें बात और है कि जो भी हम प्रयास कर रहे हैं, whatever efforts we are making, जब तक हम किसी तरह से इसको जन सहभागिता से नहीं जोड़ेंगे तब तक कहीं ना कहीं ये अधूरा होगा प्रयास. इसी कड़ी में I will like to mention just apprise here you all that last year Swachh Sagar Surakshit Sagar campaign that was interministerial was coordinated by ministry and more than 10 ministries and departments were involved in that. So you will be very happy to know that that by limited data of 75 places across the country and coast, our own institute, National Center for Coastal Research, has come up with the one paper in that impact factor approximately 7. That approximately more than 80,000 kg waste was that collected from 75 of the beaches. Out of that, approximately more than 40% was the plastic, including single-use plastic. So that was the वो एक एग्जाम्पल था जन सहभागिता का. ये आंकड़े पूरे नहीं है जो मैं बता रहा हूं आपको, ये केवल वो आंकड़े हैं कि जो हमारे इंस्टीट्यूट ने एकत्र किए 75 जगहों से, कोस्टल से. सच्चाई ये है कि लगभग 100 जगहों पर वो ये कैंपेन हुआ था और लगभग 1 लाख से ज्यादा लोगों की जन सहभागिता थी. That was just on one call by that government and ministries, and how public wants to take any that program or any activity for good cause. That is the the strength of India. That is the strength of our Bharatvarsh, that anything which comes, we can take it up and we can take it up to any challenge. So just I wish and greet you all for this talk, giving me opportunity to speak on this, particularly on Earth Day, and today is Akshaya Tritiya also Eid also. I like to greet you all for those occasions also, Akshaya Tritiya, Eid, and very happy Earth Day. Earth, Prithvi Mata हमको सब देती है, and we have to reorientate ourselves again and again for this cause of Mother Earth. So just I will like to conclude here, thanking you so much again. Thank you, Krishnan sir. Thank you, Rupa Koliji. Thank you, madam, for your beautiful poem. Thanks so much you all, and thank you very much for giving me this opportunity. Jai Hind, Jai Bharat.
Thank you so much for being with us and sparing your time, even in spite of being so busy in organizing a function at mega level.
Okay, thank you so much.
Yeah, thank you.
Just because I am at ministry headquarters, so just Ritik also has come. So there, so we'll like to leave.
So I hope to join it soon. For
Thanks
that.
a lot. Thanks a lot.
Thank you, sir. Thank you.
All
Namaskar.
the best,
Namaskar.
Jagveer ji.
Thank you, sir.
Jaiti, you may ask question from Dr. Krishnan and Dr. Rupa Kubali. Yeah.
अच्छा, एक और है, आप सभी आमंत्रित हैं. शाम को 6:30 बजे से प्रोग्राम शुरू होगा
जी.
और ये करीब 8:30 पौने 9 तक चलेगा.
अरे वाह.
ये मौसम पृथ्वी विज्ञान मंत्रालय के
जी.
We have a question for Dr. Krishnan.
Certainly, we will join you, and you are got 3-time Grammy Award winner, Mr. Ricky Cage. It is very difficult to win Grammy for once even. He has won Grammy for 3 times. So I think it is a matter of proud for us that, that he has, and also he is able to spread the message to masses about planet Earth to save it. I think he is one of the biggest example how he can make a change by his song, his message. And I think ministry has done a very right step by inviting him, because these people are really able to move the masses for, as you आपने बोला जन भागीदारी, तो जन भागीदारी के लिए हमें इतने ही पावरफुल लोगों के साथ चाहिए जो कि हमें भी मूव कर सकें और लोगों में अवेयरनेस ला सकें, प्लस टेक्निकल टॉक, साइंटिस्ट, ब्यूरोक्रेट्स, इन सब की ही साथ में बहुत ज्यादा जरूरत होती है कि हम सब साथ मिलके इस अर्थ को सेव करने का काम करें। हमने प्रॉब्लम्स तो आइडेंटिफाई कर ही ली हैं, बट सस्टेनेबिलिटी के लिए I think we'll all have to work together, right from the child to the old age people, right from technician to politician to scientist to lawyers to so students. I think this is what we are doing, and I'm glad that I've been able to bring together people from all walks of disciplines, and until now it's been so enlightening to hear on different topics. And my students are very eager to ask questions from you, Dr. Krishnan. Yeah, please, Jayati,
Sure.
please go ahead. Yeah.
Sure, madam. Yeah.
Dr. Krishnan, we have a few questions for you.
Okay.
With the increasing global warming, how has Indian monsoons moisture content and its quality is getting affected?
Yeah, so moisture content has increased in the Indian region. Also, we know that there is an assessment during the last few decades. People have assessed the water vapor has increased, precipitable water. Monsoon has the expected increase in the seasonal monsoon precipitation has not happened. It has been counteracted because of other effects of the anthropogenic aerosols. That is one of the assessment. Plus the intraannual variations caused by phenomena like El Nino. So, but we clearly, the assessment is that the increase in the monsoon precipitation due to GHG has been counteracted due to the northern hemispheric increased emissions of aerosols in the northern hemisphere. That is a very clear message that has come out of the assessment, at least during the since the mid-20th century. So if we can reduce the aerosols, especially countries like China and other places, so the immediate benefit is that is something which we can control. The monsoons are going to recover. Of course, there will be year-to-year variations. That's a different, but we are talking about really the trends in the several decades. So that's a very important, and monsoon is already recovering in the, if you see in the last few years, it has been coming back.
Thank you, sir. There's another question. What are the challenges faced during predictions of such erratic monsoon behaviors and forecasting complications? If you can give a brief.
What are the challenges?
Yes.
So the challenge is when we talk about heavy precipitation, as I said, one of the increase due to the increasing water vapor, heavy precipitation is projected to increase. But it's not a very simple, straightforward. Now, if I talk about heavy precipitation over Gujarat, for instance, people have looked at, usually it happens due to the rainstorms. Okay, these rainstorms have a scale of 50,000 kilometers or so. And when area, square kilometers. But usually when the monsoon is very active, you have the what we call as the ITCs, that the rain band is extending all the way from India. It is going up to Southeast Asia. It's a very extended rain band, and clouds are getting organized there. Convection is developing. Within this very large scale cloud band, precipitation can occur locally. And that is the challenging, how to predict those localized events, how they develop, how to predict them. That has been one of the big bottlenecks. And so it is driven by circulation. It is driven by this dynamics of these ITCs. This is an open problem. People still don't know. So heavy precipitation is a big issue, how to predict them locally, because they are going to produce flooding and so on. The consequences are going to be different. So the idea is to focus on the improve the heavy precipitation events. Tropical cyclones, we have come a long way since filing in the last several prediction skill of tropical cyclone has improved. We are able to gear up. We are able to put disaster mitigation measures, how to reduce the risks. So tropical cyclone, also to some extent heat waves. but heavy precipitation is challenging. Likewise, lightning is becoming very common. That is another challenging area. Forest fires. So according to the NDMA, these three are important targets.
How about the cloud burst? The cloud burst.
That's even more, because the time scale and the spatial scale is even more localized. That is but there is a lot. I mean, many reports are there about cloud bursts happening. So that's another area of uncertainty. So a lot of work is needed. How to improve? First, we need to get the observations for that, document them, and build the capability. Still, we are a long way, because these are happening on very, very short time scales, and increasing the awareness among the people, among the students, among the community is very, very important.
So like what kind of projects can be, what are the gap areas we can address, can be found?
Yeah. So the thing is, when we talk about these events, we need to have a good plan, how to start from the science to the development of the products, build the next generation students, and how to take it to the, for example, if you want to, when NDMA had a very nice program recently in Delhi, which I attended, National Disaster Risk Reduction. So they were focusing mainly on the community building, how to build resilience. The idea was after the big Bhuj earthquake and also the tsunami in 2004. So this idea of it started from Gujarat, and thereafter it has different SDMAs are formed, and NDMAs. They're putting this as a high priority. So interacting with the younger generation, and also communicating this message to the common public for timely action. So building those, it involves number of steps, not only science, it involves management, reducing the risk, and number of steps are involved. So that has to be, so a very, very integrated approach is needed. And first of all, we have to understand, for example, our group, we are just working on a paper on the heavy rainfall and flooding in the western part of India. Okay. So it may not, the same thing, you cannot apply it to somewhere else. So you have to evolve these strategies. So I recently read an article, Western India, how these extremes are projected based on the IPCC, based on the CMIP6 models. Very nice article by a well-known scientist. So these are going to become challenging in the future, these heavy precipitation events.
Yeah, in fact, we have a continuous digital air monitoring station also at MIT University. So
yeah, and so developing these early warning systems, that's going to be very, very important. And already MOES is doing some of these things. But for tropical cyclones, as I said, they are in a much better shape. But heavy precipitation still challenging. We need to do a lot more work. Yeah.
Even for the episodic events of air pollution which are happening in Delhi because of the parali burning, or maybe because of the dropping of the temperature.
See, air pollution now, of course there are issues, but the thing is now one of our groups in IITM, they are giving air quality forecast for NCR at 400 meter. So that's the highest resolution probably you can have. And for the entire South Asia at a 10 kilometer grid, routinely these air quality forecasts are being issued from IITM along with IMD, and they have an interaction with ICER Mohali. So you need to back up research and then science to operations. A number of things has to. So it's not one direct how. So it's we'll have to do many things to have a very integrated approach to deal with this issue.
Yeah, so I think there is a lot of areas which we can address. We can, write research projects for, to study further. For example, in Delhi NCR, at certain point, their traffic is too much. So that also, impact air pollution as well as other meteorological conditions as well. Like, for example, ozone and, like lockdown. So I think there are many gap areas which we can address, and we can work together further for it. And with IITM having the best of the facilities, I think this can
be. Yeah.
Jayati, please go ahead.
Thank you so much, sir, for addressing the queries.
Thank you.
Dr. Kohli, sir, we have few questions for you as well.
Yeah, go ahead.
First question is, how should the providers and users of climate services seek to influence global framework for climate service?
Yeah, the global framework for climate services is an activity managed at a very global level, which actually provides the concepts. But in terms of user and provider interaction, I think the best way is to have either national level or state level climate forums where they can come together, where the providers can help in raising awareness of information that they can generate and disseminate. And users can actually provide their requirements in terms of what exactly they need in deciding on climate sensitive activities. So that is how, in fact, we are trying to generate these kind of platforms, which are called national climate forums or monsoon forums, whatever way they are constructed. But this is actually being done in many countries, which is an excellent way. And it's also important for this interaction to be sustained. It is not just a one-off workshop or one-off event. It has to be continuously repeated. And in general, this is always helpful to organize this forum just before the monsoon season or some other major season that is of interest to the users, so that every year we can actually revisit the relationship and build on that. More importantly, what is required is that users should work with the providers to co-design some of the products that can be directly used. For example, you take health agencies, they can actually co-design products like heat wave index or vector-borne diseases thresholds. So these are some of the co-designed or co-developed products that can be used to be part of the routine operational activities of the providers. So this way, I think this is an iterative process. It cannot happen in one meeting. It has to be continuously sustained over a period of time.
Thank you so much, sir. And the second question is, what are the challenges at institutional arrangements and designs elements for an evaluation framework for climate service?
The major challenge is actually to bring all the stakeholders together and help them to have a common arrangement in interpreting and applying climate information. So what happens is that we have a multidisciplinary or multi-sectoral setting where a decision taken by one sector can have implications for the other sector. For example, you take water sector. So a decisions taken by the water sector in response to climate information can have an implication for the agriculture sector or health sector. So it's very important for them to have a common understanding. So this is where the National Framework for Climate Services, which can provide some institutional arrangements to make sure that this multidisciplinary or multi-sectoral dialogue or collaborative arrangements can be established. And then, in fact, the IMD is actually actively working towards creating this kind of multi-sectoral or multi-disciplinary framework that is typically called the National Framework for Climate Services. But this has to be done at a very high level, with a very high level governmental support, because otherwise, if it is done at the working level, it may not be sustainable. So it's important for us to have a high level governance support to make sure that this framework is established in the best way possible, and also it is implemented on a routine basis in an operational way.
Thank you so much, sir.
Now we have a short song composed by our very own Professor Tanu Jindal. Let us have the song.
Earth, sky, water, air, and fire constitutes a body, existence, and attire. We must bow, appreciate, admire. Love of a mother, earth to entire. Mankind and all life it's bearing. For their birth, growth, and rearing. Without obligation and complaining, with all its sources, nurturing and caring. Earth, sky, water, air, and fire constitutes a body, existence, and attire. We must bow, appreciate, admire. Love of a mother, earth to entire. Today man is so selfish and malicious, fulfilling his desires, acting atrocious. Taking out from every niche, destroying its real beauty and bliss. Downward extremes and making dams, making roads and cutting rope bands, bending heads of proud mountains, mining what they contains. Earth, sky, water, air, and fire constitutes a body, existence, and attire. We must bow, appreciate, admire. Love of a mother, earth to entire. Mankind and all life it's bearing. For their birth, growth, and rearing. Drilling holes and oozing the lifeblood, drinking fresh water, left scars on earth. Littering even the white snow sheet, glaciers are melting due to global heat. Oceans getting acidic due to dirty drains. So is acidic our once soothing rains. We must act before it destroys and burn. Earth, sky, water, air, and fire constitutes a body, existence, and attire. We must bow, appreciate, admire. Love of a mother, earth to entire. Mankind and all life it's bearing. For their birth, growth, and rearing. Earth, sky,
Thank you, Yogita, for playing it. Thank you, Yogita, for playing it. Dr. Bandyopadhyay, Dr. Shri Kunal Chaturvedi ji is, flown to Joshimath. He is at Hemkund Sahib. So he
Oh, great.
he has just phoned me. So he will join from phone for a while. So in the meanwhile, if you would like to say a few words.
I think, it's a great initiative, and the way you have invited the persons, the right type of persons for the right type of program, whether it is Jagbir Singh ji, whether it is Rupa Kumar ji, or our own Dr. Krishnan. I think everybody talked about with one language, that what is that we can do to save our art? What is the research that can be conducted in terms of controlling the different types of abnormalities that have been taking place? And in my lecture also, I just mentioned about that more important is the mitigation. And we have to go above the local level to the global level. And one planet, one earth, one life, and one environment. And that's a slogan, Vasudhaiva Kutumbakam, as mentioned by you, Dr. Tarun Jindal. I think it's very apt in the days when India has taken the presidency of G20, and all, G20 people are all talking about how spirituality can be one of the things that way to integrate the world. It is not one religion, it is not multiple of religions, but it is the spirituality where we look at the whole rather than the pieces or the parts. And we have to see that if we really want to save the whole, that is our Mother Earth. It's so needed today. Possibly, if we cannot wake up today, that is going to create us a great disasters. And your poem and your song, I don't know who actually sang it. It's a beautifully sang, by the singer. And no doubt, lyrics are very rhythmic. I must say, lyrics itself are very rhythmic. Even if you could have cited the poem, it would have been given a very beautiful feeling. And this is a great thing that I'm listening. I'm following it from 2 o'clock, and I'm listening to every speakers, their valuable comments, and then questions. The way the participant raised the questions, and the way it was handled by Krishnanji and Kohli, I must appreciate their efforts. And Jagbirji, I think he has left. He's busy in organizing the concert, and it is going to be a great concert on the particular day of art day celebration. Or overall, I could see that it is a great success. Over to Dr. Tonu Jindal.
Thank you so much, sir, for your kind words and appreciating the event. I just got call from Shri Kunal Satyarthi ji that he has flown to Hemkund Sahib and the signals are very weak. So he was willing to join through phone. We are waiting for his joining, but somehow. So I think
that he'll not be able to make it because
because Hemkund Sahib is flown through chopper and the signals are very weak. So he said, kindly excuse me. So now I request Dr. Abhishek Chauhan for the vote of thanks.
Vote of thanks.
Thank you. So once again, happy World Earth Day to all of you. Good evening to one and all. It's my privilege to offer vote of thanks and acknowledge each and every person involved in virtual deliberation on global warming and climate change, sustainable adaptation and mitigation strategy. We are celebrating World Earth Day under the aegis of Amity Global Warming and Climate Change Cluster. We are extremely thankful to our Honorable Founder President, Sir, Dr. Sokhe Chauhan, for his blessing and motivation to carry out such important program. A special thanks goes to Honorable Chancellor, Sir, Dr. Atul Chauhan, Sir, Honorable Vice Chancellor, Madam, Dr. Balvinder Shukla, for their great support and encouragement. I would like to extend sincere gratitude to all the eminent speakers for gracing this virtual deliberation and sharing us their finding and opinion. I would like to thank Professor D.K. Bandyopadhyay, sir, Chief Advisor at PU, mentor, Amity Institute of Environmental Sciences, for his view on the subject. Our sincere thanks goes to Professor Tanu Jindal, Group Additional Pro Vice Chancellor R&D, Director, Amity Institute of Environmental Toxicology, Safety and Management, for her constant support and guidance throughout the preparation of this event. We would like to thank our speaker, Dr. Jagbir Singh, Scientist G, Ministry of Earth Science, Dr. Rupa Kumar Kohli, President, Indian Meteorological Society, Dr. R. Krishnan, Director, Indian Institute of Tropical Meteorology. All the speakers for the day deliver intellectual talks and they share their knowledge. We are immensely grateful to each one of them. I would also like to thank all the participants who include scientists, technologists, academicians, research scholars, and students. I also thank all the faculty member and staff of AIETSM and AIES and NRES domain. Also would like to thank IT and personal media personnel for their support to making program successful one. Thanks, special thanks goes to our office staff, Ms. Mariamma Joseph, Mr. Rajat, and our PhD research scholars. With this, once again, I would like to thank each one of you. Thank you. Thanks a lot.